and welcome to Lessons in Logic video number 42, where we're going to learn about conditional proofs. We need, I don't know, 3 or 4 maybe, new videos on proofing to wrap up our study of proofing. I'm hoping to get those 3 or 4 videos done this morning. I hope it's 3 or 4 and I don't find out it's 5 or 6. Before we begin, just so I can have something to fill up, something nice to fill up the lower right-hand corner of the screen. This is a valley in Hong Kong's new territories. We're looking mostly north, but also somewhat east. Around sunrise, we are looking at this valley from Tai Mo Shan, Hong Kong's tallest mountain. And actually, bits of Shenzhen in mainland China are visible in the distance. All right, so send that to the lower right corner of the screen. And now, our main priority is not the beauty of a sunrise in Hong Kong so much as the beauty of logic. Let's talk about conditional proofs, which are awesome. Not as awesome as reductio ad absurdum proofs, but you have to learn conditional proofs to get to reductio ad absurdum proofs. Conditional proofs are super useful for doing proofs. Now, I'm actually not sure I can say with certainty that you can't have a complete proofing system without conditional proofs. I'm not going to sit down and think through that today. I can say that it's much better. There's a certain minimal number of rules necessary to be able to prove just any valid argument to be valid. And we have more rules than that in our proving system. Everyone does. It's a lot easier to apply proofs when you have a little more flexibility in your rules. You have more rules to apply directly to situations, because if you have the smallest possible number of rules, you have to do a lot of slow workarounds of problems. Whereas if you have rules that let you just skip through some of those problems, it's a lot easier. Never mind that. A good proofing system needs the conditional proofing rule. It's a rule that proves conditional statements. And what that means is it proves if-then statements. So I really shouldn't spend any time reviewing, or at least not any substantial time. In logic, we study how propositions relate to each other, and in most cases, how sets of propositions relate to another proposition. And in deductive logic, we study how a set of propositions, which is the set of premises of a valid argument, how they relate to their conclusion, and specifically how they guarantee it. Meaning it's not possible for those premises to be true and the conclusion false at the same time. Now, a proof is what studies that relationship of necessity, that relationship of entailment, that relationship of guaranteeing, by showing that if those premises are true, the conclusion has to follow. Now, one super useful way of doing all that is to, proofing is one super useful way of doing that. And what we do when we proof is we take the premises and then we show what follows from them, eventually showing that the conclusion follows from them. And we do it with a series of steps, each step appealing to an infallible rule, and that's enough review. A conditional proposition can be proven with a conditional proof, and a conditional proposition is an if-then proposition. So here's a sentence that's useful. We prove the truth of a conditional by temporarily assuming its antecedent, meaning we prove an if-then statement by temporarily assuming the if, and then we show that the then follows from it. Now, we don't really know, or at least we don't need to know, or it's not really part of this process to know whether the if is true. We temporarily assume it, then we show that the then follows from it, and then we show that if the if, then the then, and we don't really know or care. To be precise, we don't care. Maybe we know, but we don't care whether the if is true. So let's do a simple example. But first, let's do something a little bit different, because I don't think I've mentioned this yet, and I probably should have. Equivalence rules can be applied to parts of propositions, not just to a whole proposition. Meaning, an equivalence rule can apply to any proposition and not just to one whole premise at a time. So let me first state that I can't promise you that every logic textbook with its system of proofing rules will say, you can do this with equivalence rules. They probably should, and you certainly can. To elaborate, to illustrate, tilde means not. This is a tilde. Wedge means or. This is a wedge. And 2 tildes is a double negative. It means not. It means it's not the case that it's not the case that. So in other words, A is a proposition. A stands for whatever proposition is in the background of this argument, and we don't know or care at this point. We're assuming that someone had an argument, and it was represented in statement logic using capital letters to represent the smallest statements in the argument, the atomic propositions. All right, so A is a proposition, and tilde A is a denial of that proposition, and tilde A is a denial of that denial, which means the same thing as the original proposition. In other words, if I say A, I'm affirming some proposition. If I say tilde A, I'm denying that proposition. And if I say tilde A, I'm denying that denial. I've added a double negative, which means the same thing as the original. That's one of our equivalence rules. So here's an argument that's valid. If A, either A or B, if B, then C, if C, then D, therefore, if not A, then D. And the equivalence rule, double negation, means that not A and A mean the same thing. Now you can apply the double negation rule this way to say that either A or B means the same thing as it's not the case that it's not the case that either A or B. But you can also apply double negation to a part of that premise, or to just the A, or to just the B. So now, briefly, to illustrate this and to show that there is a way of doing this without using conditional proof, let's apply double negation and then see what we can do to complete this proof using equivalence rules, just illustrating that this is something you can do with equivalence rules. Actually, let me, here's where I give the example, the argument that we need to prove. Here's where I show you that you can prove it with equivalence rules. Let's see. So I'm going to do a double negation on line 1. And that allows me to affirm from either A or B, either not A or B. And now from that, I can use, let's see, do I have it copied and pasted? I know I meant to. Yes, there we go. I had it saved in the clipboard, thinking I would want to display it. Okay, so this is what we call the material implication rule, one of the equivalence rules. P horseshoe Q, or P arrow Q, means the same as tilde P or Q. Meaning if P then Q means the same as either not P or Q. So we can apply that rule to what we have here on line 4. So let's remember, these can go either way. With equivalence rules, you can go from the one on the left to the one on the right, or vice versa. You can go from if P then Q to not P or Q, or you can go from not P or Q to if P then Q. We're going to go from not P or Q to if P then Q. And P can be any proposition we need it to be. And here it's going to be tilde A. I do believe I feel like color coding this. Let's make that bold and red. And then let's make this one blue and italicized. No, blue and underlined. Okay. So not P or Q means the same thing as if P then Q. And P here can be not A, and Q could be B, meaning not A or B means the same thing as if not A, then B. And that's applying the material implication rule to line 4. And now, if you've been watching these videos, you probably know how to finish the rest of this proof using the equivalence rules. But again, this is just introducing one more thing about equivalence rules I should have mentioned previously. Sorry, I wish I'd had the sense to mention it before, that you can apply it to parts of a premise and not just to a whole premise at a time. Anyway, if you've been following, you probably know what we're going to do next. tilde A, if tilde A then B, if B then C, if C then D. We're trying to prove if tilde A then D. So the rest is quite simple. You can do this with, I'm thinking, two hypothetical syllogisms. A hypothetical syllogism rule twice. So if A then B and if A then C can be combined, so to speak, to give us if A then C. And that is a hypothetical syllogism rule from probably our first video on proofing, but don't quote me on that. For our hypothetical syllogism rule applied to lines 5 and 2. Remember, every line of a proof draws some inference from a previous line or lines of a proof, and it appeals to a particular rule. And the pattern of the rule, in fact, the rule itself is a pattern. That pattern in the rule, that pattern which is the rule, has to fit the earlier steps that you're applying the rule to. Let me rephrase. Every step of a proof, like steps 4, 5, 6 here and 7 coming up in a moment, every step of a proof is a tiny little valid argument in itself. And its premises are whatever steps you're using to make that inference. And the rule you're citing for that step, and you have to cite a rule for every step, that rule is the pattern of the inference you're making. Meaning, let me see if I can find an easier way to phrase this. And the annoying background noise from the vents over there, or whatever those are, the annoying noise stopped. And what I was saying is the premises for each step of a proof and the conclusion of that step of the proof fit the pattern of the rule. There, that's all. So now let's do one more hypothetical syllogism. It's a useful exercise, and usually it will tell you what you don't need to look at anymore to see what steps you've already cited. We've already cited steps 1, 4, 5, and 2. So 1, 4, 5, and 2, we can probably just ignore. And as it turns out, as I look now at lines 3 and 6, the only ones we haven't used yet, I see they're telling me if tilde A then C and if C then D, and that really does get me directly to the conclusion. So the hypothetical syllogism rule is if P then Q, if Q then R, therefore if P then R. So now, following that same pattern, if tilde A then D on lines 6 and 3, if tilde A then C, and if C then D, therefore if tilde A then D. And that gets us to our final conclusion. All right, so that's how you can do this proof using some equivalence rules. But now let's do it with the conditional proof. Here is what it would look like. Apparently I've worked it all up before, and I probably should have deleted some of this text, but I guess I'll just go over it instead. So now conditional proofs are like this. You prove the truth of a conditional statement of an if-then statement by temporarily assuming its antecedent, by assuming the if part, and then showing that the then part follows. So in this argument, we're told if either A or B, if B then C, if C then D, and we're trying to prove if not A, then D. So to prove a conditional proposition with a conditional proof, you just assume the first part, the if part, the part that's to the left of the arrow, where the arrow means if then. And then you show that the then part, the next part, the part to the right of the arrow follows. Now, how does it follow? Quite simple. Assume tilde A, and you'd have to label it as an assumption. This is one line of a proof. This is the only line of a proof that does not appeal to an infallible rule yet. It's a temporary assumption. And oh my goodness, I need to say this explicitly. You have to identify it as an assumption, not only by having this line labeled assume, or a slightly different proofing system would say assumption, or if you want, you could call it a temporary assumption, or whatever you like. It doesn't matter much, unless your teacher's a real stickler for one particular way of phrasing it. But also, it's good to indicate where the assumption begins and where it ends. Now, the conventional way I'm used to is to have these lines here, but not all of them. What I'm used to is the lines would stop right about there. They aren't a whole box. But in preparing my notes at some point in the past, I didn't know how to do that on Microsoft Word, and I didn't know how to make a box. Right now, I don't know how to make the box either. So it's possible that I'll just tab it over a bit, which is a perfectly useful strategy in future. In fact, I'll tab this over and keep the box later in subsequent parts of this video or in subsequent videos. Maybe I'll tab it and not use the box. Anyway, what was I saying? This is the one line of a proof where you don't actually have to appeal to an infallible rule, because this is not actually a conclusion. With a proof, what you're doing is you're showing what follows from the premises, ultimately showing that the conclusion follows from the premises. And every line of a proof that does that has to appeal to an infallible rule. But this is not a line of a proof that does that. Line 4 here is just making a temporary assumption. It's going to be a temporary premise that we can use for other things that fall within the scope of that assumption, only these things. And then that will allow us to show that from that assumption, such and such follows, and therefore, if that assumption, then what follows from it. I'm just noticing now a terrible typo. Let's fix it. There we go. Okay, so back to the proof. Either A or B, if B then C, if C then D. We're trying to prove if not A then D. So we temporarily assume not A, and what follows? By the disjunctive syllogism rule on lines 1 and 4, we can conclude B. Disjunctive syllogism rule is either P or Q, not P, therefore Q. So either P or Q, not P, therefore Q. You see how we're following the pattern of disjunctive syllogism rule to get this conclusion. B follows from tilde A. Now, we don't know that tilde A is true. We don't know that B is true. So far, all we know is that tilde A, if tilde A then B, follows. Now, that's not what we really want, although we could actually close out our assumption there. Maybe I'll illustrate that in a moment, but let's do it this way. By disjunctive syllogism on lines 1 and 4, we get B. And now by modus ponens on lines 2 and 5, we get C. If P then Q, P, therefore Q. Or if B then C, B therefore C. Very simple, modus ponens. Now do the same thing, modus ponens, with the C that we just have. If C then D, C, therefore D, by modus ponens on lines 3 and 6. That shows us that D follows from tilde A. So when you close off the proof, you indicate that you're done with this temporary assumption, and you show that and you state that the last thing in that proof, in that temporary assumption, the last thing in that temporary assumption follows from the first thing. And you should always do it this way. You should always have this pattern when you're doing a conditional proof. Now, just a moment, I'm realizing I don't have the actual pattern here. Just a moment. And here we are. Here's the generic pattern of a conditional proof. Now, if your brain's like mine, you look at this and you have difficulty knowing what it even means. But basically it means at some step of a proof, we assume a thing. We temporarily assume a thing, all hypothetically. What if this were true? And then we see what follows from it. And then when we get to the thing that follows from it that we need, we say, if that first thing, then that second thing follows. And then we say so, and we say we're citing the conditional proof rule on that whole exercise. So that's the generic form of the rule. But let's go back to what we were working with. I was trying to summarize the pattern you want to work with. Okay, so the pattern you want to work with is, for a conditional proof, you're making a temporary assumption that the if clause of an if-then statement guarantees the then clause. Oh, sorry, I phrased that wrong. You're trying to prove that, you're trying to prove an if-then statement. You're trying to prove that the if clause of an if-then statement really does guarantee the then clause. You're trying to prove that the if-then statement is true. So you assume that the if part is true and you show that the then part follows. Let me start this over again. I'm trying to say something about the form. We're trying to prove tilde A, if tilde A, then D. If tilde A, then D. So we temporarily assume tilde A, we show that D follows from it, and then we state that if tilde A, then D, citing the whole process of getting from tilde A to D. And the pattern should be this. The pattern should be the first thing in the conditional proof, the temporary assumption, should be left of the arrow, or if using different symbols, the horseshoe, in the first line after the conditional proof. There's going to be some premises. There's going to be a conditional proof. The first thing in the conditional proof needs to be given immediately after the conditional proof. And right where you give that thing, you don't give it by itself, give it as an if-then statement. And the second part of the if-then statement is the last thing in the conditional proof. The temporary assumption of a conditional proof should be the antecedent to a proposition. The last line of a conditional proof should be the consequent to the proposition, meaning the if clause and the then clause. And you should give that particular if-then proposition right after the conditional proof. There, I think I finally said it succinctly. Sorry. Let me just uniformize my citations because I like the way I'm doing it here better than the way I was doing it here. So that was a DS on lines blah, 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 and then modus ponens on lines blah, 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 and again modus ponens on lines, etc., etc. And we're done. That's a good conditional proof. Let's see if I said it succinctly here. We have some premises, we make an assumption, we label it as an assumption, we see what follows from it. So we conclude that that really does follow from it. Or we make an assumption, P, we label it as an assumption, we see that Q follows from it, then we conclude that Q follows from P, or P arrow Q. Then we announce that we've proven this conditional statement using the conditional proving rule. And to make sure that we don't think that anything within the scope of the assumption is guaranteed by the premises, we bracket off the entire thing. The only thing the premises guarantee is what you conclude from this assumption. You can't assume anything here is guaranteed by the premises. You can only assume that what this whole assumption proves, namely the if P then Q, or in this case, if tilde A then D, you can only assume that that conditional proposition follows from the premises. Let me rephrase that one more time. These things do not follow from your premises. They follow from the premises plus the temporary assumption. But since we don't know the temporary assumption to be true, we can't export any of these automatically out of our conditional proof. Instead, what we get to export out of the conditional proof is if this, then this. And we could have said if tilde A then B. We totally could have done that. Speaking of which, let's do it a different way, because I like that way. I'm going to try that. Let's do this proof in a different way. If A, either A or B, if B then C, if C then D, therefore if not A then D. So temporarily assume not A, and that gives us B by disjunctive syllogism on lines 1 and 4, and that allows us to conclude if tilde A, then B by conditional proof lines 4 through 5. And now using tilde A arrow B and then B arrow C and C arrow D, we can get to tilde A arrow D, same as we did before. Hypothetical syllogisms. if tilde A, then C, by hypothetical syllogisms on lines 8 and 2. And then if tilde A, then D by hypothetical syllogism on lines 9 and 3. So there's two different versions of a conditional proof for this argument. Now let's do one more simple example. If M, then if L, then D. Also, if M, then L. Therefore, if M, then D. Now, how do you prove that? Well, we can make a temporary assumption. Let's go ahead and tab it over as well as bracket it. Now, what follows from M? Now, I'm going to use not the Beatty rule. Let's work forward because I'm looking at this and I can see it's going to work out very nicely. Also, I looked at it earlier and noticed it would work out very nicely. So what follows? Here is the working forwards practice, which is usually not recommended. My recommended strategy is usually the Beatty rule, work backwards. But sometimes just look for what you can see that will move things in some direction that will allow you to conclude something from the premises. Sometimes that is a useful strategy. Sometimes here it will work. So what can you get from one of these premises and M? Well, it's quite simple. You can get L from lines 2 and 3 by the modus ponens rule. And also you can get if L, then D by modus ponens on lines 1 and 3. Hey, good. I'm glad this came up. Note how on line 4 here, we cite lines 2 and 3. So I occasionally say you can usually assume that you're not going to use a line of a proof more than once, but there are exceptions. So usually if you've used a line, you can assume you're probably not going to go back to it. But this is one of those exceptions because you have to go back to line 3. Don't cross them out. You don't need line 2 anymore, as it turns out, but you will need line 3 again because you need to use line 3 for the modus ponens on line 1. Now, the rest should be fairly simple. M, where's UD? Well, it looks like we can just do a simple modus ponens again on lines 5 and 4. And then I think we're actually done with the conditional proof. We just need to say we're done. We need to show, we need to state that since the assumption of M led inevitably to D, if M then D by conditional proof on lines 3 through 6. And that's it. That's the conditional proof. Now, the most obvious use of a conditional proof is to prove your conclusion when your conclusion is itself a conditional statement. But you can use your conditional proof to get to other kinds of conclusions. And here's how. You can only directly prove a conditional statement with a conditional proof rule. In other words, once again, the conditional proof rule always has this pattern. It's the pattern we were illustrating here with these symbols P and Q here. But the pattern is the first assumed step of the conditional proof is the antecedent to a certain proposition. And the last step of a conditional proof is the consequent to the same proposition, and the statement of that if-then statement, the antecedent arrow consequent proposition, is given after the conditional proof, and it cites the conditional proof. So you can only directly prove a conditional statement, an if-then statement, with the CP. But once you have that conditional statement, you can use it to derive other statements. So can you think of a proofing rule that allows us to convert a conditional statement into another kind of statement? And I ask that, and then I think, gee, I've already showed them in this very video. Which rule allows us to convert a conditional statement into another kind of statement? I believe you'll find it right here. the material implication rule will allow you to convert a conditional statement into a disjunction. All right, and I think we are finished with this video. See you next time with more proofing.